In this video, we will see the key geometric result behind the ellipsoid method. For now, our ellipsoid method will be an algorithm to decide whether a polyhedron is empty or not. Our polyhedron is denoted by P, and it is the set of points in Rn that satisfy the system of linear inequalities Ax greater than or equal to B. Later on, we will also see how the ellipsoid method can be used to solve optimization problems of the form minimize C transpose X subject to Ax greater than or equal to B. But for now on, let's just focus on the feasibility problem. The first thing we need to do, if we want to introduce the ellipsoid method, is to define ellipsoids. Intuitively, ellipsoids are the high-dimensional version of the two-dimensional ellipses. In this picture, we have an example of a three-dimensional ellipsoid. Since ellipsoids will be truly fundamental in this chapter, let's define them formally. The first thing we need to define are positive definite matrices. An n by n symmetric matrix D is called positive definite if X transpose Dx is strictly positive for all non-zero vectors X in a Rn. Note that X transpose Dx is a quadratic function, so in particular it is not linear. From the definition of positive definite, we immediately obtain that the positive definite matrix D is non-singular, therefore we can consider its inverse, which you can show is positive definite as well. Now we are finally ready to define an ellipsoid. An ellipsoid is a set of vectors in Rn that satisfy x minus z transposed D inverse x minus z less than or equal to 1, where D is a positive definite symmetric matrix and z is a vector in Rn which is called the center of the ellipsoid. We denote this ellipsoid by EZD or simply by E. A very special type of ellipsoid is the ball. A ball centered at Z and of radius r is defined as the ellipsoid E of Z r square I, where I is the identity matrix. If we use the definition of ellipsoid, we obtain that this is the set of points in Rn that satisfy x minus z transpose times x minus z less than or equal to r square. Therefore, the set of vectors x in Rn that satisfy 2 norm of x minus z less than or equal to r. We are now ready to explain intuitively how the ellipsoid method works. Let's visualize this in a picture. This is our given polyhedron P, and our task is to decide if it is empty or not. Of course, from the picture we already know that the specific polyhedron is non-empty. But generally, when we're given a system Ax greater than or equal to B, we don't know if the corresponding polyhedron is empty or not. The first thing that the algorithm does is to generate an ellipsoid which is guaranteed to contain the polyhedron P. Now the ellipsoid method at each iteration generates a different ellipsoid. So let's focus on a specific iteration and let's say that the latest ellipsoid generated is ET. Now the ellipsoid ET is guaranteed to contain the polyhedron. Next, the ellipsoid method looks at the center of this ellipsoid. We denote this vector by xt. Then the algorithm checks if xt is in the polyhedron or not. If it is in the polyhedron, then P is non-empty and the algorithm terminates. Otherwise, it means that there exists a constraint that defines P that is not satisfied by the vector xt. In our picture, an example of such a constraint is this linear inequality here. As you can see, it is one of the inequalities that defines P, and the vector xt doesn't satisfy it. Next, our ellipsoid algorithm translates this inequality so that it passes through xt. Now the original inequality was valid for P, so the new translated inequality is valid for P as well. Now we look at the set of points in the ellipsoid ET that satisfy this new translated constraint. Since this translated inequality passes through the center of the ellipsoid, we call this region a half ellipsoid. Next, our ellipsoid algorithm finds a new ellipsoid that is now called ET plus 1 that contains the half ellipsoid that we just discussed. Since in turns the half ellipsoid contains P, also the new ellipsoid contains P. Now the remarkable feature of the ellipsoid method is that it guarantees that the volume of the new ellipsoid is only a fraction of the volume of the previous ellipsoid. You can see now that repeating this process, either we find eventually a point in the polyhedron, or we keep generating smaller and smaller ellipsoids. Eventually, the volume of the ellipsoid becomes so small that it allows us to conclude that it cannot contain any polyhedron and therefore that P is empty. This last step is perhaps the most surprising at this point. It is based on the fact that the volume of a non-empty full-dimensional polyhedron cannot be smaller than a certain threshold. So when the volume of our ellipsoid is below this threshold, we can conclude that it cannot contain any non-empty polyhedron. The next theorem is rather technical, but I want to show you the statement because it gives us an analytical formula of the new ellipsoid. And it also gives us explicitly the ratio of the volumes of two consecutive ellipsoids. Let's read through theorem 8.1. Let E of ZD be an ellipsoid in Rn, and let A be a non-zero n vector. Consider the half space H of the vectors x in Rn that satisfy A transpose x greater than or equal to A transpose Z. Now let Z bar be equal to Z plus 1 over n plus 1 dA over the square root of A transpose dA. And let d bar be equal to n square over n square minus 1 times d minus 2 over n plus 1 dA A transpose D divided by A transpose dA. Now the matrix d bar is symmetric and positive definite. Therefore we can consider the ellipsoid E prime equal to E of Z bar d bar. E intersected H is contained in E prime, and the volume of E prime is equal to the volume of E times E to the minus 1 over 2 n plus 1. We will not prove this theorem. However, this makes you understand that the ellipsoid method can compute the new ellipsoid by calculating Z bar and D bar. It also highlights one problem that we will consider later on. Namely, in computing Z bar, we have one square root, and this means that potentially we could be dealing with irrational numbers. And this is not good because you know very well that for us it's very important to consider the size of the vectors that we are constructing. And if a component of a vector is irrational, then its size is essentially infinite. So for now, forget about the square root, we're gonna talk about it later.